Hello, this is Dr. Gardner. Today we're going to be looking at what goes on within solids and liquids and gases. What we'll be focusing on in this chapter is the interactions between particles of different types, including atoms, ions, molecules. As we start to look at these interactions, these interparticle forces and molecular compounds, we might call them intermolecular forces. We'll be considering the strength of these forces and the energy changes as we might change between states of matter. We're going to begin with looking at changes between solids, liquids, and gases, and some of this might be a little bit of a review, but we want to be looking at what's going on at the smallest levels with the atoms, ions, molecules, as well as the energy changes that are occurring as we go through these changes in states of matter. In more advanced courses, we might look at phase diagrams, but we won't be focusing on that in this particular chapter. Now, first of all, if I consider what is holding my particles together in a substance, well, we have potential energy, that's energy due to position. What's going on is we have attraction between particles. This is really a Coulombic type of attraction, so we can think about Coulomb's law. Coulomb's law is looking at the electrostatic force, that's the attraction between dissimilar charges. So if I had charged species A, it's going to be attracted to charged species B, so I can say the electrostatic force is directly proportional to the magnitude on charge A and B divided by the distance squared. So the further apart these charges are, the weaker this interaction is. As they become closer, they have stronger interactions. The magnitude of charges, well, let's think about that. With ionic compounds, as you start to have complete electron transfers, we're going to get complete charges of +1, +2, +3 or higher. Potentially, the higher those charges are on the ions, the stronger they might be attracted to one another. That could dictate solubility. So very highly charged ions, especially if their sizes are small, so they can be in close proximity to one another, so that the distances are also small, gives us a very strong electrostatic force of attraction. So we end up with those ions being very strongly held together. So we have to overcome that with high energy. So their melting points and boiling points are very high. In some cases, some ionic compounds might dissolve in polar solvents like water, but if the attraction between the charges are too strong, with high charges and small sizes of the ions, we may end up with insoluble compounds. So it can relate to solubility of compounds as well. But really, it's all about these electrostatic attractions. Even when we look at molecular compounds, even though they don't have a permanent charge, they haven't completely transferred electrons to form ions, they do have charges between the molecules depending on their polarity. So polar molecules are going to have a stronger electrostatic attraction than nonpolar molecules, but not as strong as an ionic species. If I have a nonpolar molecule, you might think that there could be no electrostatic attraction, but you'd be incorrect. We'll see later on that the electron clouds can distort on occasion, and we'll have some specific names we're going to be giving that in our future discussions. But right now, realize my potential energy when I'm looking at these particles attracting one another is going to be related to these electrostatic forces and that Coulomb's law of attraction between charged species. Now, if I consider that those are the interactions occurring that are drawing compounds together to be more likely to form liquids or solids, well, what causes your compounds or your particles in different substances to be separated from one another as they go from the solid state to the liquid state to the gas state? Well, this is going to be related to their kinetic energy, the energy of these particles related to their motion. So the kinetic energy of my atoms, ions, molecules, or particles I'm looking at will be directly related to 1/2 the mass of the particle times its velocity squared. So as I increase kinetic energy in my samples, I can achieve that, for example, by increasing temperatures. So if I increase the temperature of my sample, the average kinetic energy of the particles, whatever they might be, starts to increase. Now, there's still a distribution of energies of the particles. Some of the particles will be moving slower than others. There'll be an average velocity of these particles, and then some will be moving faster. This is why, for example, when you're looking at water at room temperature, it will slowly evaporate because some of the particles at room temperature are moving at high enough velocities that they can start to overcome the potential energy of the electrostatic attractions to go to the gas phase over time. But the average of our kinetic energies is lower than that, and so we're looking at this distribution of kinetic energies but that kinetic energy is this energy due to motion. As I increase temperature, the average energies start to shift to higher average energy. So the speeds of the atoms or molecules or ions start moving faster, and they can potentially overcome the electrostatic attractions between the particles, and that might disperse them. So if it's high enough, we might go between a liquid to the gas phase and have a great change in the distance between the particles. So we might end up with having a lot of empty space between the particles if we have a high enough kinetic energy to disperse those particles and overcome their attractions between one another. In fact, when we were treating gases as ideal gases, we assumed that we could ignore the attractions between them. We had already at those temperatures overcome the attraction between those particles. In some cases, if we're talking about gases at room temperature, well, the electrostatic attractions might have already been weak, like with non-polar gases, like carbon dioxide, nitrogen gas, oxygen gas, noble gases, and those situations. Now, if I'm looking at the different states of matter, solids, liquids, and gases, we might want to think about the properties between them. In general, here I would like you to look at the pictures of my solids, liquids, and gases and the spacing between the particles. So if I'm looking at a solid, we tend to have very little spacing between the particles, and if we have what's called a crystalline solid, we have nice organized rows of the particles in the crystalline solid. So a molecular crystalline solid, like your sugar crystals in your kitchen, might have molecules in each of these fixed positions, but they're nice and organized in a crystalline solid with a repeating pattern three-dimensionally. Now, I can also have amorphous solids. Amorphous, so morph means shape, amorphous means without shape. An amorphous solid, such as you can have with silicon, for example, would have a disorganization of the solid particles. But even in that case, whether I have a crystalline solid or an amorphous solid, I'm going to have the solid particles in very close proximity to one another. Their kinetic energy tends to be low compared to the other states of matter for that substance, and so there's very little motion to them. Now, that doesn't mean they're completely motionless. They actually have a little bit of vibrations between them. In fact, you can kind of think about this as like elementary school students when they're sitting in their chairs. There's a little bit of wiggle to them, even if they have assigned seating like we might have in a crystalline solid. So there's some motion going on there, but they don't have enough kinetic energy yet to start to overcome their assigned positions in the solid entirely, despite the vibrations that are occurring. At higher kinetic energies, they might be able to start to overcome some of those electrostatic attractions. They can start to slide past one another, but they still stay in close proximity. That would be like going through your melting point between the solid to form a liquid. So there's a lot more freedom of motion in the liquid, but they're still in very close proximity, keeping the distance between the electrostatic attractions fairly close together. However, if I go from a liquid to a gas, in the gas state, we have a high enough kinetic energy that we start to overcome the electrostatic attractions between the particles to a much greater extent, and we end up with them dispersing the particles, so there's a large amount of distance between them. So if I'm looking at these different three states of matter and we want to classify their properties, well, if I have a gas, there's a lot of empty space between each of the gas particles. The gas will expand to take on whatever volume of container you give it. So you can think about gases, they're kind of space hogs. They'll take as much space as you give them. Okay. Now, since they'll increase in volume till they reach the volume of the container that's confining them, well, they also tend to conform to the shape of that container. We can say the compressibility of gases is very high. That's because of all the empty space between the gas particles. If we put a higher pressure on there, we can compress the gas particles closer together. In fact, we can continue compressing the gas particles until their pressure reaches a high enough quantity that the gas would start to condense and potentially form a liquid. In that case, the particles are close enough together that their electrostatic attractions become strong enough, and they're in close proximity that we end up perhaps with the liquid state of matter. They also have the ability to flow as gases. They can go ahead and flow readily past one another, all that empty space. We're overcoming the electrostatic attractions. That makes complete sense. Now, we can also talk about what are condensed states of matter, or condensed phases of matter. If we want to ask what a condensed state or phase of matter is, that's going to be a state of matter that has very little compressibility. So both liquids and solids are considered condensed states of matter with very little compressibility between the liquid and the solid. Now, the reason for this is because whether I have a liquid or a solid, the particles, whether they're atoms, ions, or molecules, tend to be in very close proximity to one another, so there's not a lot of empty space when I'm looking at my liquids or solids. Remember, if we look back at our pictures here, the gases are very compressible because of all this empty space between the gas particles. Your liquids, though, there's not a lot of empty space between the particles, so I can't compress liquids very readily. And solids also have very little space between the particles, so I can't compress solids very much either. So those are my condensed states of matter that have very little compressibility. Okay. Now, if I'm looking at liquids, they also have the ability to flow. They can slide past one another. Now, I can often talk about the ability of a liquid to flow related to a term called viscosity. Viscosity is the resistance of a liquid with respect to its ability to flow. So if we consider, let's say, cold pancake syrup. Cold pancake syrup is a very viscous liquid. It would pour very slowly onto your pancakes. The attractions, the electrostatic attractions between the particles end up being strong enough, and at the cold temperature of the cold pancake syrup, they're not overcoming those attractions very readily, so there's a gradual flow. However, we notice that viscosity will change as the temperature increases. Let's think about why. Why does warm pancake syrup flow more readily than cold pancake syrup? Why would the higher temperature pancake syrup be considered to have a lower viscosity? The reason for that is as you heat up the particles in the pancake syrup, the molecules, we start to have a higher kinetic energy. We have more motion between the particles as we start to overcome more of the electrostatic interactions with that higher kinetic energy, and the average velocity is increasing. As that occurs, we are able to overcome electrostatic interactions more readily. We start to have the molecules sliding past one another. As they do so, the viscosity drops. So we expect viscosity, but temperature usually decreases in most situations. With respect to that, that's kind of important. In fact, if you consider your motor oil that you might use in your cars, your motor oil will often have a viscosity rating, whether or not it's rated for different temperature ranges, for their low temperature or high temperature ranges for the operation of your engine. So viscosity is very important with respect to proper choice of engine oils. So that's something we'll look at. So the liquids definitely can flow, but they may have varying viscosities. Very polar liquids tend to have high viscosities, especially at low temperatures. Non-polar liquids would tend to have low viscosities, whether the temperature is low or high potentially. Not very compressible, condensed state of matter. Liquids tend to conform to the shape of the container, and they're limited with respect to their volume and by the surface that they have to work with. So basically I have a consistent volume with liquids, whereas gases have a very variable volume. Whereas solids also maintain a specific volume, but they also maintain a shape. Liquids might conform to whatever shape their container has, but a solid will tend to maintain whatever shape it began with. Now, there's almost no compressibility with solids or liquids. That's why we were calling them condensed states of matter. With respect to solids, they also don't really flow because, remember, we tend to have fixed positions. Especially with the crystalline solid, we have organized repeating patterns in 3 dimensions with very fixed positions between the solid particles. Okay, so these are the general properties you should know for gases, liquids, or solids. On our next exam, I might ask you to list these. So make sure you know all of these different properties to identify your gases, liquids, or solids. The next thing we want to consider is what do we use for our terminology when we just talk about changes between states of matter, or what I might call changes in phases of matter. Now, when I talk about a phase of matter, let's define what that means. A phase of matter is a very physically distinct, homogeneous part of a system. Okay, now homogeneous means it's uniform throughout, right? So if I look at my phases or states of matter, we're talking about, for the most common states that we deal with in a chemistry laboratory, gases, liquids, or solids. Now there's other states of matter like plasmas out there that I'm not focusing on right now, and some other more exotic forms you might talk about in a physics course, but right now we're going to focus on the forms that we deal with most frequently on the lab bench in the laboratories. So gases, liquids, and solids. If I'm looking at between the changes in these states of matter, let's consider what I would name these changes in phases or states of matter. So if I have a gas going to a liquid, okay, well, I might want to consider what's going on in that situation. A gas going to a liquid, my average kinetic energy is decreasing as I cool my sample down. In that situation, we call that condensation. So a gas going to a liquid is condensation. Let's consider going the other direction. If I heat a liquid up until it overcomes some of the intermolecular interactions of the liquid, and then we end up dispersing the particles to have extra space between them as we're heating it, what would we call that process? So we usually call that evaporation, or you might call it boiling, like when you boil water. Okay, so That's the terminologies we would use for those two, and you're probably very familiar with those terminologies. Now let's consider if we take a liquid and continue cooling it down, drawing off heat energy, and so the average kinetic energies are decreasing, we end up with a greater organization of the particles, and we start to form a solid. As that occurs, we could call this process freezing. Now, if I were to heat up a solid, and so we start to overcome some of the intermolecular interactions until we have more freedom of motion and the particles are starting to slide past one another, but they're still in close proximity, we could end up with that solid forming a liquid. In that case, we would call that process melting, but there's another term that we'll be using that you might not be as familiar with. We can also call this the fusion process. So if we talk about the heat of fusion, the energy it takes for a fusion process, we're talking about a melting process. Okay. Now, you may not have been familiar with fusion, but the other terminology you probably were pretty familiar with your everyday lives. Now, sometimes we can have states of matter changing directly between gases or solids and gases without becoming a liquid in between. Now, when this occurs depends on what temperatures and pressures you're dealing with. In more advanced courses, we use what are called phase diagrams to predict when these changes directly between gases and solids might be occurring without passing through the liquid state. We will predict with a phase diagram when that occurs depending on your temperature and your pressure conditions. Now, if I have a gas going directly to the solid state, the terminology for this, let's think about what that means. A gas going directly to the solid, that would be a deposition process. Okay, so if you live somewhere cold in the winter, such as Idaho, you might go ahead and notice that sometimes you come out and it may not have snowed, but you might have frost on your windshield. And so we might have that ice on your windshield that may have occurred from basically water vapor in the air directly going through a deposition process and forming a solid on the glass surface. Okay. Now we can also have the reverse process. If we have a solid going directly to a gas without forming a liquid in between, well, that would be a process that we call sublimation. We should be familiar with all these terminologies as we discuss these. Now, the most common example of sublimation might be at a party if you have dry ice. Let's say you put dry ice in a container full of root beer. What we can have happen there is the dry ice is actually frozen carbon dioxide. Now, the frozen carbon dioxide, when we're dealing with atmospheric pressure, doesn't actually form a liquid state. It goes directly from the solid to a gas, so it goes through a sublimation process. Okay, so there's another reason for calling it dry ice, even though it has nothing to do with water solid state that we normally call ice. Okay, so that sublimation would be the solid CO2 going directly to carbon dioxide gas particles. And as that happens, you can cause carbonation. You can have some of the CO2 dissolving in that root beer in your container at a party, and you end up with having the carbon dioxide forming a little carbonic acid, and you're getting all of the fizz and the bubbles of the CO2 being produced in the root beer during the party, plus the dry ice is cooling down the drink as well. So kind of interesting. So you should be familiar with deposition, sublimation, and all of these different terminologies for changes in state of matter. Now that we are all making sure that we discuss changes in states of matter with the same terminology, let's focus on looking at the energy changes when we have changes in states of matter. Now, if I have to overcome intermolecular interactions as I go through a phase change, we're going to have to put heat energy in. When I put heat energy in, we're going to have a change in what we call enthalpy, where we're putting heat energy in to overcome those interactions. So when I have a process where I'm putting heat energy in to overcome my interactions, that could be a melting or fusion process. So I could say that the change in enthalpy was positive, meaning I have to put energy in, so I have a positive change in internal energy of my system. Or I can have vaporization, so I get a positive change in enthalpy. A delta here represents the Greek letter delta capital, represents a change in the value after it, just like when we talk about changes in temperatures, delta T's. Well, the delta H, we're going to have a change in the enthalpy value. When we have the not symbol here, that represents standard state conditions. Don't worry too much about that right now, but we can end up with having to put energy in through a melting or fusion process as well as vaporization. Now this makes sense. Think about when we have a vaporization process. When we have vaporization, we have your particles, let's say, in the liquid state, and as we increase the kinetic energy, we start to disperse those particles, and they have greater space between them as they go to the gas phase, and as we have that phase change or that change in state. With respect to after that change in state, now we had to put energy in to overcome those attractions. Imagine pulling two particles apart that are attracted to one another. It's not quite the same where we're talking about electrostatic attractions here, but you could maybe imagine having two bar magnets and trying to pull those apart. You're putting energy into the system as you try to pull those magnets apart, so your potential energy is increasing as you pull them apart, as you put in more kinetic energy. So as we're doing that here, we're pulling those particles apart and we're putting energy into the particles to disperse them. Okay, so that's going to be a process that we consider is endothermic. So we put heat energy into the system in an endothermic process to overcome those attractions. Now sublimation is the same way. In fact, I have to put as much energy into a sublimation process as I would have to put into the fusion and vaporization process combined. Now that makes sense. We can talk about enthalpy changes as state functions. If I have a state function, it doesn't matter the steps I go through between the beginning and the end of the process for a state function. All I care about is the initial state and the final state. Now this makes sense here, because if I say that the energy I put in for the melting process and vaporization process would add up to the sublimation energy, that makes sense because I begin at the same state, the solid state, and I end up at the same state, my gas phase, and the same amount of energy must have been put in overall. Okay, so I can just add up an enthalpy of fusion and an enthalpy of vaporization, and they would add up to my enthalpy of sublimation. Now, if I have an exothermic process, that means heat energy is given off to the surroundings. And when I have exothermic processes, for example, would be when the particles start to lose their potential energy and exchange that for kinetic energy potentially as they become closer together and the electrostatic attractions start to become more significant with close proximity. That would occur during a condensation. So if a gas condenses to a liquid, let's say my gas from a hot shower condenses on my mirror in my bathroom. In that case, that's an exothermic process. I'm releasing some of the energy from the gas particles to the surroundings. The mirror and the surrounding air and the surrounding materials that are nearby as it goes through condensation. So the change in enthalpy here is negative. So exothermic processes have a negative sign for the enthalpy changes, and endothermic processes have a positive sign. Okay. As I go from a liquid to a solid in a freezing process, well, that is also exothermic, releasing heat energy to the surroundings. This is why you have to cool down a sample to draw off that heat energy as you go through these phase changes. Now, a deposition process would be the same energy change as condensation and freezing combined. So if I added the enthalpy of my condensation and the enthalpy of my freezing, we'd end up with the enthalpy of deposition. Now, I want you to notice that if I were to determine the enthalpy of vaporization, since I'm just going the other direction with my phase change, if I just change the sign of the enthalpy of vaporization, the negative of the enthalpy of vaporization would be the same as the enthalpy of condensation. And if I change the sign of the enthalpy of fusion to a negative value, that would be the enthalpy of freezing. The negative sign just tells me I'm giving off heat energy rather than taking it into the system. With a deposition process, as I go from a gas to a solid, that's just the reverse of sublimation. So if I just change the sign on the enthalpy of sublimation to a negative, we would get the enthalpy of deposition. Okay, so that's what we're looking at here. When we look at these enthalpy changes, we will look at units of energy per mole. So I have to consider the sample size in moles, usually. Sometimes you'll notice that our sample sizes might be in grams, but energy per mole is common, or energy per gram. Here we'll use the term joules, or in fact we're going to use thousands of joules, so kilojoules per mole. So usually we'll look at values of enthalpy in kilojoules per mole. Okay, now if I want to add up the enthalpy of fusion and the enthalpy of vaporization, now remember fusion is melting, and the enthalpy of vaporization is when we have your liquid going to the gas state. If I add those up, well, then we can define the enthalpy of sublimation, and we can use a technique that's called Hess's law, where we can say that each of the individual steps in this change can be added up to be the same as the enthalpy change for the overall process. So if I just add up enthalpy of fusion and enthalpy of vaporization, I get the enthalpy of sublimation. Okay, they're a nice additive process. Okay, so I'd like you to consider pausing the video here, and as a class I'd like you to discuss, without looking back at the notes, which of the following phase changes would you consider to be exothermic. So go ahead and pause the video and discuss this. Okay, so once you've had a chance to pause the video and discuss this, I want you to be thinking about this process. If I have an exothermic process, my particles must be having their electrostatic attractions, bringing them in closer proximity, or reducing the amount of movement between them as you start to have that electrostatic energy to holding them together, and you have less and less kinetic energy in this process. If I had an endothermic process, I'd be putting heat energy in and increasing the average kinetic energy of my sample and potentially going between solids to liquids and liquids to gases. So if I look at this, if I talk about vaporization, if vaporization is going to be a liquid going to a gas, I'd have to put energy in for that to happen, so that would have to be endothermic. A sublimation process would be the sum of my melting or fusion and then my vaporization, so that's also endothermic. I have to put heat energy in to overcome those intermolecular interactions as I go directly between the solid state to the gas state. Now condensation, on the other hand, would be taking a gas and going to the liquid state. As I go from a gas to the liquid state, I end up with my average kinetic energy decreasing, and I must give off that energy somewhere, and so I give it off to the surroundings in an exothermic process. So your correct answer in this case should have been C for the condensation process being exothermic. Now let's think about that. If you're sweating and you end up with water on your skin from perspiration, as that water evaporates, as you go through a vaporization process, it's cooling down the surroundings, it's cooling down your skin, and so your body's using that as a method to cool itself down. And if it's cooling itself down, it must be, in that case, the phase change of the liquid water to the gas phase water must be absorbing heat energy from your skin, so that would definitely be an endothermic process. So that might help remind you that condensation, the reverse process, would be exothermic, which is also why you might find it quite unpleasant to be in very hot weather, but where it's also humid, right? Because you're not able to remove as much heat energy from your skin from having evaporation of moisture off of your skin. Okay, so let's look at a few of these energy changes here briefly. If we're looking at the change between the liquid state to the gas state, we expect that's an endothermic process. So if I take liquid water and I vaporize it to form water vapor, my enthalpy change, my delta H, is endothermic, which I have a positive sign for. Whenever I'm in an endothermic process, I'm putting energy into my system. My system is the number of water molecules I'm looking at going between the liquid to the gas state. So I'm putting energy into them as I disperse them from the liquid, and they have further distances on average between them in the gas state. We've overcome electrostatic interactions, and that causes them to be dispersed and be further apart. In this case, I'm actually overcoming hydrogen bonding, as we'll talk about later in this chapter. Now, the amount of energy I have to put in, if I measured it, would be 40.7 kilojoules of energy for every mole of water that goes through this vaporization process. Now, when I say that the enthalpy change with this not symbol here is under standard state conditions, what my standard state conditions would be 1 atmosphere, and it would be at the boiling point for this liquid. So at 1 atmosphere, my boiling point for water would be 100 degrees Celsius. Okay. And let's consider a melting process. It's also called fusion. So the heat of fusion will also be endothermic. I put heat energy in, so it has a positive sign for my endothermic process here. I could have the solid going to the liquid state as I have this melting or fusion process going on for, let's say, an ice cube melting to form liquid water. Now the enthalpy change for fusion is 6.01 kilojoules per mole. Now I want you to think about this. If the vaporization is 40.7 kilojoules per mole, but the heat of fusion or melting is only 6.01 kilojoules per mole, why is there such a large difference between these two energies? Maybe pause the video here for a second and discuss why that would be the case. Okay, once you've paused the video and thought about that as a class, let's see if you came up with a reasonable answer here. Now, if you thought about going between the solid and the liquid state, still having condensed states of matter, where your water molecules are still in close proximity to one another, well, then you can realize that I only have to overcome enough of my electrostatic attractions, or in this case with water, my hydrogen bonding, my attractions between particles, that I end up with them more freely moving and sliding around one one another in the liquid state, but they're still in close proximity that I don't have to put in nearly as much energy. However, if I want to take liquid water and go to the gas phase, I have to pull those water molecules really far apart. I have to overcome much more of the electrostatic attractions to increase the distance on average between particles. So it takes a much larger amount of energy. Hopefully that kind of makes sense to you with respect to why there's a much larger heat of vaporization than for fusion, and you should expect that in all samples of all substances that the vaporization process are much more highly endothermic than your fusion processes. Now let's consider if I have a condensation process. My condensation process would be the gas-based molecules or the gas-based particles going to the liquid state. Now that's going to be an exothermic process, so I'm going to have a negative sign for the change in enthalpy. That exothermic process is going to end up giving off heat energy to the surroundings as I end up with the water molecules, in this case, becoming closer together to form a condensed state of matter to form a liquid. Now, in fact, the energy change here is just the exact opposite of the vaporization process. So if I know the enthalpy of vaporization, I know the enthalpy of condensation. It's merely the negative of the enthalpy of vaporization. I just changed the sign. The flow of energy is going the other direction in this exothermic process. So I have a negative 40.7 kilojoules per mole. Now I'd like you to memorize that negative enthalpy changes are exothermic and positive energy changes are endothermic. If you can remember those two situations, that's going to make your life quite a bit easier. Okay, now if you think about heats of freezing, okay, the heat of freezing is just the opposite of your enthalpy change for your fusion or melting process. So if I take the negative of the enthalpy of fusion, which was my melting process, well then that would be my heat energy change for the freezing, but now that's going through an exothermic process rather than endothermic. So a negative 6.01 kilojoules per mole would be my enthalpy change during a freezing process here. Very nice, because if I just give you enthalpy of vaporization, you also know the enthalpy of condensation if you just change the sign. Or if I give you the enthalpy of fusion or melting, I know if I just change the sign there, I get the enthalpy of freezing for the reverse process. Quite nice how that works. Now I want you to ask yourselves, and maybe you should pause the video for a second here, but what would be the value for the heat of sublimation of H2O? So sublimation of H2O. Okay, so if you're wondering what this means, the sublimation, remember that's going from the solid state directly to the gas state. So what would be the heat of sublimation? Well, in this case, we could go ahead and take the enthalpy of the two steps involved energy change-wise with respect to sublimation. Now, sublimation is a solid going directly to the gas phase, but it doesn't form a liquid in between. However, the energy change is the same as the summation of adding the heat energy change of melting and vaporization. So a fusion and vaporization. So if I just added 40.7 kilojoules per mole of water going through this process for the vaporization process, as well as 6.01 kilojoules per mole for the melting process. If I add those two up, we get about 46.7 kilojoules per mole for the sublimation process. Okay. So what you might want to do is have a little class quiz. In some of my on-campus classes, I have iClicker quizzes, but let's go ahead and have a little class quiz here. Okay. What would be the heat change, the enthalpy change, for the heat of deposition? So if I had the heat of deposition, what would be the energy change that would be going on here? Okay. So I really want to know what is the delta H of deposition. Okay, so pause the video and see if you can answer that question. Okay, now the choices I'd like you to pick between are either positive 40.7 or negative 40.7 kilojoules per mole, or positive 46.7 kilojoules per mole, or negative 46.7 kilojoules per mole. Now my heat of deposition, my deposition process will be going directly from the gas state to the solid state. That energy change should be the same as my enthalpy changes for the individual steps you could imagine with respect to these processes. So the energy change is identical to if I was going through condensation and then going through a freezing process. Okay, so if I look at condensation and freezing, I get a negative 40.7 kilojoules per mole for the condensation process. My freezing process would be a negative 6.01 kilojoules per mole. Now, despite the fact that I'm not actually forming a liquid in deposition, I started at the same point and ended at the same point. So if I have a state function, as we mentioned before, the change in energy is still identical to any other steps that could be taken to go between those two states. So I can go ahead and add up the heat of condensation and heat of freezing, and so I should end up with D at negative 46.7 kilojoules per mole. Okay, so for today we'll end there, but I want you to review and read through your chapter on the heats of phase changes. And the next time we'll be looking at cooling and heating curves and calculating the energy changes involved as substances are heated and cooled and go through phase changes, as well as take into account changes with respect to specific heat calculations. So if you've forgotten how to perform specific heat calculations from earlier in the semester, you probably want to go back and review specific heat calculations, because it'll make our next lecture discussion much more readily understood. Okay? Have a great day, everybody. Take care.